Hi, my name is Philip.
What's up?
Bartek,
Shiv,
Amelia,
Alex,
Mario,
Jamie,
Matthew.
And we are the Imperial Planetary Robotics Lab, or IPRL for short. We are a new team formed at Imperial College London, and we are part of the Imperial College Space Society. This year we are competing in the European Rover Challenge as our first goal and first milestone, and in this video we'd like to present to you our rover, the Harbinger. We are a UK team, but few of us had to already leave the UK for the holidays. That's why Harbinger is being finalized in a few places at once. So in this video we will take a slightly different approach and actually take you for a tour all around the globe to see how our work is progressing. Our first stop is our headquarters in London.
Welcome to EEE 505, the Robotics Lab, where student imagination and chaos come together. This is where the Harbinger, like many other robots, was born.
We created IPRL to support students looking for opportunities in planetary robotics and science by building test projects for them to test their skills on. The ERC is a difficult competition for us to enter. However, it gives us the experience and credibility for us to continue moving our planetary robotics project forward.
We keep our team as small as possible to minimize communication issues and maximize our efficiency. Therefore, we also keep a flat team structure, and the project was broken down to clearly divisible responsibilities so that each sub-team lead is clear about what they and the others are doing, allowing them to also specialize in their field. Now, off to Bartek to tell you more about the electronics which drive Harbinger.
The energy subsystem is broken down into two parts. The first one is the one that powers the robotic arm, and the second one is the one that delivers electricity to the main motors and all the necessary sensors. Each subsystem has a relay which is controlled by the Arduino Mega board, so that we can actually control the power remotely. Naturally, we also monitor the power consumption of each of the electronic subsystems, and apart from that, each subsystem has an array of fuses which stop an excessive current from flowing into the sensitive devices. There is also a physical safety button installed on the rover, which cuts the power delivery completely in case of any failure.
Hello again. Let me tell you about how the remote control works.
First, let me tell you the main component of the Harbinger to be controlled. These are the arm, which will play the main role in the maintenance task, and the cheese wheel for the movement. If we take a look inside the rover, we can see the two comm systems set up for the remote control. The secondary comm system is composed of the 2.4 GHz nRF24LL1 module connected to the Arduino Mega. This can perform basic transmission but has low bandwidth. The primary is composed of the Raspberry Pi connected to a 5 GHz router outside of the rover. This has high bandwidth and can provide images or video if necessary. The Mega is connected to the motor drivers and the arm to control the components. The status of the components and the rover can be shown by the ground control station. The station will be a laptop with a front end made by React, which will contain the video feed, velocity, orientation, along with other information. Analogous info screens will also be shown for the status of the arm.
Harbinger has a double rocker mechanism suspension based on 4 wheels, which providing a rigid contact attachment point on all 4 wheels. This design was chosen as it compromised well between complexity and reliability. To actuate the rocker, a differential bar was created in contrast to a gear differential to minimize backlash and increase system stiffness. Apart from suspension, each wheel can rotate individually, allowing rover differential steering. With the combination of motors and gearboxes, the rover speed on ground is limited to 0.45 meters per second maximum with its own weight. On top of this, the wheel possesses symmetric tread patterns that offer greater directional stability. Sending you back to UK.
Harbinger features a 4 degree of freedom manipulator to address the science and maintenance tasks. The manipulator is powered with a number of NEMA 17 and NEMA 23 stepper motors with built-in planetary gearboxes to increase accuracy and torque. The arm is made mainly of laser-cut folded aluminium with steel shafts and 3D printed transmission elements to minimize mass and cost. The transmission is performed by pulleys and tying belts to further increase the torque if needed and to allow for the motors to be positioned at the beginning of links rather than near the joint. This reduces the unloaded torque that the arm has to overcome. To control the arm, we implement a number of preset positions corresponding to task requirements, such as a stowed position, interaction position, or gathering position. These allow for ease of operation and reduction of time when performing tasks. To do this, we rely on closed-loop control at a motor level and inverse kinematics at a manipulator level. From there, we rely on visual feedback from a camera positioned on the gripper to ensure the task is carried out accurately.
Two identical containers are attached in front of the rover. The load cell with the amplifier with high precision measures the collected sample's weight up to 600 grams by finding difference in mass.
The rover uses a 360 camera to continuously scan the environment for Rover codes. We use the OpenCV library to detect the codes, then refer to a dictionary of known positions and orientations to estimate our own position. Each code can point in 4 possible directions, and multiple codes can be detected simultaneously. We reconcile the different measurements by probabilistically weighing the different positions and choosing the highest weighted one. This gives us an estimate of both the position and orientation of the rover.
The science task requires a suitable landing site that is scientifically interesting and technically feasible. We chose an area near Flaker Mountains, which offer intriguing insights into the planet's mineralogy and presence of water ice. Various geological studies and analysis have provided evidence of volcanic activity, water ice deposits, and tectonic processes in the region, which we hope to explore more.